Okay, this lesson is our second lesson on counting principles, permutations, combinations. So this is where we're actually going to introduce factorials and permutations. We're not doing any kind of new questions, but we're going to use a tool that will help us solve some existing questions, and we'll start to explore some more existing questions that really get to be very complex. So in the first unit, we only explored two different pathways through through a Pascal's triangle, sorry, a tree diagram. Um, but now we're actually going to see a lot more different pathways. And so I really like this quote from Robert Frost, just this idea of thinking about like how way leads on to way. And really that's what we get is these tree diagrams that we can't even count the number of pathways. And so we do need techniques to help us with that. So here's a question that's very famous that we do in class. And so it's just this idea that, so if you have 26 people, what is the probability that at least two people share the same birthday? And so we've got these options. We get students to think about it. And so you can just take a thought. What would your gut reaction be? So would it be less than 10? Like not very likely. Would it be 10 and 20? Like it's not very likely, but it could happen. Same with between 20 and 30. Or are you thinking like it might be like between 30 and 50 or even higher than 50? So the big idea doesn't change. It's just this idea of like making informed decisions, managing risks. So we're learning probability techniques to do that. A learning goal today is using the fundamental counting principle to calculate theoretical probabilities with more than two events. And then you can recognize when factorials are used in counting number outcomes, recognize when permutations are used, and then use factorials to calculate permutations. So those are all the things we're going to learn today. So this is a really famous question, the birthday paradox. And so I'm not going to play this in this video, but like I just invite you to like YouTube, what is the birthday paradox? It's a really interesting idea. And so the guy actually does it on stage, and so he's asking people what their birthdays are. So it's kind of neat to listen to these mathematicians do it. I also like in the video that he talks about just like he's having trouble counting, and so he's just kind of making the point that mathematicians are mathematicians. It doesn't necessarily mean that they can't make mistakes with arithmetic. So here's the birthday problem. So this is what you have to consider. And so this is back to the Robert Frost kind of quote about way leading on to way. So you've got to think about two people have the same birthday, and then how many ways that can happen. So you're sharing a birthday with somebody or anybody, and then somebody else is sharing with somebody or anybody, because each student can share a birthday with every other student. You could also have three people sharing a birthday. It's not as likely, but you could have two people sharing a birthday and then two other people sharing a birthday, so two pairs or even three pairs. So it's all these different cases. And so when we notice that, like whenever there's so many cases that we really can't even count them, we can't figure it out, like slot method's not really working, there's always like this like kind of indirect way that we want to think about. So this like idea that we can't count the direct cases, like the number of ways people can share a birthday, but we could count the indirect ones. So here's like kind of like the solution for it. And so N of S is the total number of ways that students in the class can share a birthday, or can have a birthday, not share. N of A prime is the total ways that students have a different birthday. So notice the subtle difference there, like have a birthday and then have a different birthday. And so there's 26 slots for having a birthday. And so you can imagine there's a slot for every person. We got to decide how many ways that each person, we don't know who they are, we don't know what their birthday is. So there's 365 different days that they could be born. And just for the sake of argument, we ignore leap years for a minute, but 365 different days. 365 for the second, third, fourth, all the way to the 26th person. And so you guessed it, we can calculate that by using an exponent, 365 to the 26. And then a different birthday, we can again put 26 slots down. Remember, if we have 26 slots for N of S, we probably have that for every other case as well. So, and 26 slots for every student again. Except now the first person does have 365 ways, but now we'll say that they can't share with the second person. So the second person only has 364. The third person only has 363. So you see where we're going here? Like everyone has to have a different day. So we're losing a day every time we slot somebody. The fourth person only has 362 ways, 341, and 340 because we're not counting the other days that those students are born. And we're going to find out we can calculate this by doing 365p26, which means 365 is the start. And we're going to multiply by one less every time until we get 26 numbers. And so this will be 26 numbers total. 365p26 will be the way to calculate. Now your calculator does have a button for 365p, and it'll be like NCR. And so where you can actually calculate these separate 365 to the 26, it will allow you to take this number and divide by this number, because the numbers are just so big. You might even need a spreadsheet to do it. And so continued, we can divide them now to find out the probability that we don't have the same birthday. And so if we divide those, we actually get 40%. And so if you were thinking over 50% before, you'd be right. There's 59.8% chance that 26 people share a birthday. And now when I do this in class, like every once in a while, like every other one, like is not a match, and it's like kind of boring. It's not as exciting. But when there's a match, it's kind of neat. It's really powerful to see. And it should be a match if we have a class of 26 in 60% of classes. So now we got to go back to like where that p come from. And so first we kind of answer this question, what is a factorial? And so if we ask how many ways to arrange 4 people, there are 4 slots and 4 ways to put the first, 3 ways to put the second, 2, 1, and then so it's 24. The way to write that is 4 exclamation mark. And so factorial actually means we take the number and then we multiply by 1 less all the way to 1. And that's what the exclamation mark does. And it only works for n as a positive integer. Here's another interesting look at just how big factorials can be. And so I really love this, and you can YouTube this math magic. And this is from Vsauce, and I won't play it in here, but it's just like so powerful talking about how big the number 52 factorial is. And I love the analogy with cards. You can never shuffle, if you shuffle a deck of cards perfectly, totally random order, chances are, he says, that you'll never get that same order in the history of cards. Not you, or not that deck of cards. There's never been in any deck of cards, which is really cool. Permutation is actually kind of like a factorial. And so, but what happens is we cut off the last bit. And so we don't go all the way down to 1. And so the permutation is the number of arrangements of R objects taken from N. So taken from a total. And so we've already seen 365 and then taking 26 people out of that. And it is an arrangement of distinct objects in a specific order. So how can we use permutations to calculate factorials? Say for a second you need 5 lowercase letter password. We can't repeat the letters. How many ways could that happen? So we'd have 5 slots, and then it'd be 26, 25, 24, 23, 22. So this is actually 26p5. But what the calculator is doing when it calculates it, I just want you to understand, is like they're trying to get rid of, so if 26 factorial equals this, or 26 factorial equals this, 26 20 to 22 to 21, and then 21 all the way down to 1, you need to find a way to stop multiplying at 21. The way to stop multiplying by 21 is like really to undo it. And if you want to undo multiplication, so take it down all the way to 1 and undo it, you just divide them out. And so we just take 26 factorial and divide by the 21 factorial. And if you wanted to like write those out, you could actually cross them out and you could see them like crossing out. Here's an example. So we got 40 people entered in a raffle, 7 family members for 5 different prizes. So we want to find out what the probability is that all the prizes go to the 7 family members. And so N of A is, you can start with N of S or N of A. So N of A is 5 slots, 1 for each prize winner. So there's 5 decisions to be made, 5 prizes to give out. And we have to give them out to the 7 family members. So you got 7, 6, 5, 4, 3, or 7p5. So 7p5 will calculate it for you, or you can just type that in. N of S is 5 slots, but now we have 40 for the first one. 39, 38, 37, 36. So that's 40p5, which is 78 million. And it's not a very likely chance, of course, that your family is going to win all the prizes. You can imagine that. It's a point zero zero zero, I think, like, and then it after you times by 100, you get 0.0032%. This is a really neat problem that I kind of created. And so this toy that my son has is called a cotapillar. And so the question was like, what probability could we ask for the following? And so like you kind of understand what this thing is doing. And so I paint it better in class. And so there's a picture of it on the first in the first unit. So there's actually 8 different random like things that he can attach. And you can see like the body of the caterpillar is different. It's a caterpillar, but it like works for coding. You can see the body is a little bit different every time, and so you can actually put them in any arrangement. And so I'm just going to kind of turn the sound off because I can play these all at the same time, and I'll talk it through as I'm playing them. And so what happens is like there's 3 of these straight arrows, and you'll notice that like, and these are all going the same direction. Just the middle one is still going through the same tunnel. You notice that the middle one there like just veered off and didn't actually go through the tunnel like this guy on the right. To go through the tunnel, what he had to actually do was he had to have 3 straight arrows in a row. Over here, you can see this music box happened, but the 3 straight arrows led him through the tunnel. Because this guy had a sideways arrow, like one of these arrows, he actually veered off. And so the question that we're going to ask is like, what's the probability he's going to go through the tunnel? They're all going the same distance. The big thing is, what's the probability that you go straight, 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 and then something else? Or, and there's where the music box comes in. The music box is involved in those straight arrows, but there's 3 straight arrows anyway. And so it's a really neat question to kind of think about and explore. Um, you do have to know that there's 8 different pieces, 3 straight arrows, 1 music box, and then 4 turns. And you can put them in any order you want. And so I just thought it was a neat question. If you're not going to solve it, I just thought it was a really neat question to start thinking about probability in a more concrete way. So here's some questions. And so this is a good one here. So really a big idea is like that sometimes like some questions are related to others. So like rearranging the letters in the word factor could be the same thing about as like rearranging people in a picture. And so like the question is like, could you make a birthday problem that doesn't really involve birthdays? So it's like just the probability that 2 people are the same in something else.